Hi, welcome to science123.co.uk, a website created for GCSE and A level students, created by experienced UK tutors and examiners. Ionic equations are used to show what is happening only to the ions actually involved in a chemical reaction, and it leaves out those that are not. The ones that are not involved are known as spectator ions, as though they are only watching the reaction. We only use ionic equations to represent the reactions of ionic compounds when they separate into their constituent ions and react. They leave out the clutter of other ions that may be present but are not changing in the reaction, so we can focus more easily on what is happening. So should you always write an ionic equation if there's an ionic substance involved? Well, probably not actually, given that they are one of the most difficult types of equations for students to write. So look carefully at what you are being asked to do and only use an ionic equation if specifically asked to do so. Some ionic equations are quite easy to write. For example, the reaction between an acid and an alkali, where you can see here the H plus from the acid reacting with OH minus from an alkali, making water. If you need to construct an ionic equation, you will first need the full balanced symbol equation. And if you are asked to do so, remember to include state symbols. This is how the previous example for the neutralization reaction was derived. Here is the full balanced symbol equation, including state symbols. Notice that nearly everything in the equation is aqueous, which means dissolved in water. These are ionic substances which will dissociate or separate into ions in water. However, H2O is shown as a liquid. This is because it is covalently bonded and therefore does not dissociate into ions. So remember, we only dissociate ionic compounds into their respective ions. Covalently bonded substances do not contain ions. They are non-metals bonded together. You need to be able to recognize these in equations, with the most common examples that you will see being carbon dioxide as a gas, and we've already seen H2O as a liquid. But there are also ions that contain covalent bonds within them. For example, nitrate, which contains covalent bonds between nitrogen and oxygen. There's carbonate and sulfate, etc. We do not split these. So let's look at the neutralization example again. Here is the full balanced symbol equation with state symbols. Splitting the reactants first of all, HCl contains a H plus and a Cl minus ion, one of each, sodium hydroxide and an Na plus and an OH minus ion. Looking at the products, sodium chloride produces a sodium and a chloride ion, but the H2O, remember, is a liquid and covalently bonded, therefore it does not split into ions. Next, we look for spectator ions. Remember those that are not changed in a chemical reaction. On both sides of the equation, shown in red, we have a chloride ion, and we also have, shown in yellow, a sodium ion. We therefore take those out, which leaves H plus OH minus in the reactants and just the H2O liquid as a product. This is our overall balanced ionic equation. Ionic equations are particularly useful for representing what is happening in displacement reactions. Remember, this is where a more reactive metal can displace or push out a less reactive metal from its compound. In this example, we split the copper sulfate and magnesium sulfate into their respective ions because they are ionic. The solid magnesium and copper remain unchanged. They contain metallic bonds. Next, we look for spectator ions. They are, remember, the ones that are unchanged on both sides of the equation. Here we just have a sulfate ion. Removing them leaves the final ionic equation. More advanced students will be required to write ionic equations for the reaction of H plus from acids with substances other than alkalis, such as with metals, oxides, and carbonates. By the time you reach your exam, you may be able to write these quite effortlessly, but if not, you will need to be able to derive them. As an example of a reaction between an acid and a metal, let's use magnesium and hydrochloric acid. Notice in the full balance symbol equation that there is a 2 in front of the HCl. Each one will release a H plus and a Cl minus. Looking for spectator ions, there are 2 Cl minus on each side of the equation, which we take out, leaving the balanced equation shown. Always check that charges are the same on each side of the equation, as this is usually a giveaway that something is wrong otherwise. Here we have 2 plus on the left, 2 plus on the right with the Mg2 plus. The charges are the same, therefore. They do not have to be zero. For the equation between an acid and a metal oxide, let's use a reaction that you've probably carried out yourself. I'm sure every student has made blue copper sulfate solution. Here we have sulfuric acid, H2SO4, reacting with copper oxide solid. Copper oxide is very insoluble in cold water. However, when you add it to warm sulfuric acid, I'm sure you can remember seeing it slowly dissolve and react. We therefore need to split the copper oxide into its aqueous ions to derive the ionic equation, along with the sulfuric acid and the copper sulfate solution that is formed. Looking at the full balance symbol equation and the formula of H2SO4, we can see that this contains 2 H plus ions, but only 1 sulfate ion. Copper oxide contains 1 copper 2 plus ion and 1 oxide ion, O2 minus. Looking at the products, the copper sulfate forms 1 copper 2 plus ion, 1 sulfate ion, SO42 minus, and liquid H2O. Next, we look for spectator ions, which are those that are the same on each side of the equation. They have not taken part in the chemical reaction. So we have 1 sulfate ion and 1 copper 2 plus ion on each side, which we then remove to leave the overall ionic equation, which is the 2H plus from the acid, the oxide ion O2 minus, forming H2O liquid. Finally, the reactions between acids and metal carbonates. Here is an example, which is again similar to one which you may have carried out yourself. You may have carried out a reaction between acid and marble chips. Marble chips contain calcium carbonate, as shown here, but this time I'm going to use nitric acid. Here is the full balance symbol equation, which you will need first of all. But just as we did with the metal oxide, we need to split the insoluble ionic metal carbonate into its respective aqueous ions when it reacts with acid. This ionic equation is probably one of the most difficult that you will see, simply because there is balancing required in the overall equation and there are brackets in some of the formulae. So looking at the first line, we have 2 nitric acid. Looking at the products, for calcium nitrate, we can see there are brackets in the formula, and you need to understand what these are telling us. So we can see there's an NO3, which means there's a nitrate ion, where the nitrogen and oxygen are covalently bonded together. But after the brackets, there's a 2, meaning that we have 2 of these nitrate ions overall. Dissociating, the HNO3 releases a H+, but we have 2 of them. This means we also form 2 nitrate ions. The calcium carbonate splits into 1 calcium 2 plus ion and 1 carbonate ion. In the products, we have 1 calcium ion, the 2 nitrate ions, carbon dioxide gas, and H2O liquid, which remain unchanged because they are covalently bonded. As for previous examples, we now look for spectator ions. On both sides of the equation, we have two nitrate ions and one calcium 2 plus ion. We remove those, which leaves as the reactants 2H plus and one CO3 2 minus. In the products, one carbon dioxide and one water molecule. Here is a summary showing the reactions of acids as ionic equations. In the first line, we have the reaction of an acid and an alkali. In the second line, we have the reaction of a metal with an acid, using magnesium as an example. Then an acid and a metal oxide. And then finally, an acid and a metal carbonate. Remember to check that your equation balances, including for charges. I always check the charges first, because if these do not balance, then there is clearly an error somewhere in the equation. Can you now derive an ionic equation from a full balanced equation? Try to come up with examples of your own. For example, pick a metal and an acid and see if you can derive the balanced ionic equation. You could head over to our website www.science123.co.uk to find lots of our mini GCSE and A level courses, which are being added to all of the time, as well as individual and group tuition options. We are also starting to offer residential courses. You could also subscribe to our channel, where you will be notified of our latest releases. Thank you.